Hello, welcome to my talk on the history of aerodynamics, Part 3, the Age of Fruition in the theoretical aerodynamics. This period covers almost all 20th century. As I have talked in Part 2 on this topic, up to 1906, all the necessary principles for aerodynamics were in place. However, how to use these principles to solve the practical problem is a different issue. In the first half of the 20th century, researchers worked on this series and solved many practical problems, and some of those methods are still being used today. The second half of the century is mainly the computer age. Computers have been used to solve very complicated problems. Today, if we use CFD to solve an aerodynamic problem, we may not think about the Joukowski theorem or CUDA condition in our numeric modeling. Only in the panel method, this may be still required, but they were of vital importance when used the potential flow theory to solve the aerodynamics problem, especially the problem with the lifting bodies. Let us have a look at the achievement at the very early 20th century. In 1903, the Wright brothers made their first successful heavier-than-air flight, and less than a year, in 2004, they made a closed-circuit flight, and in the same year, Prandtl developed the boundary layer theory, which is still in use even in the modern CFD modeling. And in 1906, Joukowski theorem was established. Up to then, all the necessary principles were in place. After that, it is a period how to use and improve the theory, especially before the computer age. Here are some key achievements in the modern aerodynamics are listed. In 1909, Louis Blériot flies across the English Channel from Calais, France to Dover in England. In 1910, Joukowski proposed the Joukowski transformation and the Joukowski airfoil. In 1915, Prandtl established the lifting line theory, and in the same year, NACA was established. In 1922, Munk developed the thin airfoil theory for calculating the lift and the moment acting on the airfoil. In 1925, Prandtl's mixing length theory was developed, and in 1928, Prandtl-Glauert compressibility correction was established. In 1933, Theodorsen's general potential flow for arbitrary airfoils using the conformal mapping method. In 1947, the first supersonic flight was made by Bell X-1. In earlier 1960s, researchers studied the panel methods for calculating the airfoil, wings, and aeroplanes. In 1970s, turbulence models such as K-epsilon, K-omega models for CFD have been developed and accepted. In 1990s, large Eddy simulation has been used for studying the turbulence flow. And in 1997, hybrid LES was proposed by Prandtl. The Joukowski transformation is given by this. Here, A is the radius of the reference circle. See here the red circle. So to create a Joukowski airfoil and modified and shifted circle, zeta prime is calculated as this. So this would be given in this blue circle. Here R of it's the distance between the center of the original circle, the red one, and that of the modified blue circle. So this parameter is used for control the Joukowski airfoil thickness. And the delta is the shifting angle here. See the figure. This parameter is used for controlling the camber line. This plot showing the original circle in green and the modified circle in blue, and the Joukowski airfoil in red. From this Joukowski airfoil, we can see this airfoil has a curves at the chilling edge. This might play the limit for the Joukowski airfoil. For solving the problem, Carmen Tafez made the transform in 1918, which could generate the much broader airfoil for practical application. The idea behind the Joukowski transform is that there is an analytic solution for the flow around the circle with a certain circulation. This can be expressed as the uniform flow plus a circulatory flow with a circulation, capital gamma. So the combined flow would be the circle with a circulation, gamma. And we can see the stagnant points on the circle are not symmetric anymore due to the existence of the circular flow. So here the stagnant point and here. So such a type of flow, we have the mathematical or analytic solution for this type of flow. So if we apply the Joukowski transform or called conformal mapping, use this formula, and we can have the flow past an airfoil, the Joukowski airfoil. And we can see from this plot the stagnant point at the leading edge and the stagnant point at the chilling edge. And the flow would be separate from the chilling edge. This is in coordinates with the Kuta condition. The Prandtl lifting line theory or the Lanchester-Prandtl wing theory is a mathematical model for predicting lift distribution of a 3D wing based on its geometry. See here. So this lift line theory states that the lift over each wing segment, the local lift per unit span, does not correspond simply to the 2D analysis product, but also is strongly affected by the neighboring wing section. So we see this bound vortex and the distribution along the span of the wing. The lifting line theory is based on the concept of circulation and the Kuta-Joukowski theorem. It produces the lift distribution along the span wise based on the distribution of the bound vortex. So the overall lift on the wing is given by this integration from tip 1 to tip 2. Thin airfoil theory is a simple theory of airfoil in incompressible inviscid flows. It was developed by Max Munk in 1922 and further refined by Prandtl-Glauert and others. The theory idealizes the flow along an airfoil as a two-dimensional flow along the thin airfoil. More specifically, the airfoil is represented by the camber line and the airfoil has a zero thickness. Since the study is in the incompressible and inviscid flow, thus the airfoil fraction is not included. By applying the Coulter condition, we can obtain the vorticity distribution. See the drawing here. Thus, we can derive the lift and moment acting on the airfoil. The thin airfoil theory was very important because it provides the sound theoretical basis for the following properties of the airfoil. The center of the pressure and the aerodynamic center are coincident and lie at the quarter of the chord behind the leading edge. The theoretical lift coefficient for thin airfoil is given as this simple equation. Here, alpha is the angle of attack in radians, and CL0 would be 0 for the symmetric airfoil. Take an example of the thin airfoil NACA 009. The prediction using the thin airfoil theory is in black line, and the dot and dashed line is from the experiment data. This for the lift coefficient, and this is for the moment coefficient. So we can see when the angle of attack is small, say less than 12 degrees, the thin airfoil theory predicts the lift and the moment very well. See the comparison here. In 1925, Prandtl studied the molecular shear stress in fluid. See the figure here. So he could determine the shear stress Txy in terms of the mean flow velocity Uy and the fluid turbulence viscosity μT, given in a form as this. And based on the Prandtl's proposal, the mixing length theory, the fluid turbulence viscosity is given as this. And here, air mix is the mixing length. It needs to be specified in the actual simulation. So this, in a way, would limit the application of the Prandtl's mixing length theory. For this approximation model, it is still quite useful for providing a tool for solving some specific turbulence flows, if the mixing length air mix can be specified. This model can be used for enhancing the basic understanding of the turbulent flow and provide the basics for the later development in Prandtl's one-equation turbulence model. This model has found the applications in different areas, including atmospheric science, oceanography, and stellar structure. In the 1920s, researchers have worked on the high-speed flows. In 1925, the linearized supersonic aerodynamics was developed, and in 1928, Prandtl-Glauert made the correction for the compressibility, and in 1940, the application of the supersonic flow theory has been made, and in 1947, the faster than speed of sound flight, Bear X1, was made. In the development, an important advancement was the Prandtl-Glauert transform, or Prandtl-Glauert correction, was established based on the linearized equation with the compressible inviscid flow, and the correction was made for the pressure coefficient Cp given by this. Here Cp is the pressure coefficient with the compressibility, and Cp0 is the pressure coefficient for the incompressible flow, and M0 is the free stream Mach number. Obviously, we can see the Prandtl-Glauert collection has a singularity when m0 equals to 1.0. See this figure. When m0 equals 1, Cp would be infinite. If we look at this picture, we can see the sonic boom around the aeroplane when the aeroplane passes the sound barrier. That is, the Mach number is 1.0. So the sonic boom might linked with the singularity of the pressure coefficient at Mach number m0 1.0. Theodorsen was a Norwegian-American aerodynamicist who was famous for his contribution in the theoretical aerodynamics, as well as his studies for turbulence. In 1933, he developed the general potential theory for arbitrary wing section, in which he built the method for transforming the arbitrary airfoil into a circle, such that he could extend the thin airfoil theory and the Joukowski transform. Both were limited to the specific cases, but the general potential theory can be used for any airfoil and even other different body as well. So in summary given by Theodorsen, the transform or the conformal mapping to transform the arbitrary airfoil in the zeta plane into a circle in the Z1 plane here. There are 3 steps in the transform. The first step is transform the arbitrary airfoil into a circle-like closed curve in the Z prime plane here. And use the further transform. This circle-like curve can be transformed into 4 circles in the Z plane. And the last step is the shifting made from Z plane to Z1 plane by shifting a distance C1 here. And from this transformation, we can see the flow direction to the airfoil here is alpha, but the flow direction for the circle in the Z1 plane is alpha plus beta. So all these transforms are quite complicated, but it is workable even without the computer. This method has been also used by Apple for designing his airfoil. See the reference 2. With the digital computer available for computation, the panel code was developed from early 1960s. The advanced panel codes such as Prandtl, developed by Boeing, was first introduced in the late 1970s, and such panel method has been very popular even with the great advancement in CFD. Panel codes are still used for preliminary aerodynamic analysis because of its fast turnaround time and the reliable prediction for some parameters. There are some basic assumptions for the panel method, which are basically based on the potential flow, in which the flow is assumed to be irrotational and inviscid. And for such flows, CUDA condition must be satisfied on the lifting surfaces. For the incompressible potential flow, the normal Laplace equation would be used given as this. and for the compressible flows, with the assumption of the small disturbance on the main flow around the x-axis. So the dynamic equation for the potential function phi for the supersonic flow given as this, and for the supersonic flow, the dynamic equation for the potential flow is given as this. Also, the dynamic equation for the compressible flow has a different dynamic equation for the potential function. Use some specific coordinates transform, we can still write the dynamic equation for the potential flow in subsonic and in supersonic to be a form as the conventional Laplace equation. Hence, all this flow can be solved using the Panner method. Details can be found in the relevant textbooks or in my talks later. Powerful computers in 1970s were made for the implementations and validations of the proposed turbulence model possible, and thus provided the opportunities for tuning and enhancing the turbulence model. Therefore, in 1970s, the turbulence models have been well established and well accepted. This including the famous two equation turbulence models. K-epsilon model. The first K-epsilon model was formulated at Imperial College in late 1960s and tuned and enhanced in 1970s. The transport equations for both turbulent kinetic energy K and the dissipation rate epsilon are both directly derived from the Reynolds averaged Navier-Stokes equation. And since then, the K-epsilon model has gained widespread use since 1970s. And the enhanced model were available, including the renormalization group RNG and the realizable model, and many other variants. The first K-epsilon model was proposed by Kolmogorov in 1942 and independently by Selfman in 1970. Wilcox kept improved Selfman's K-omega model since 1970s. The K-omega model getting popular since the Mentor's SST K-omega model in 1994. This SST model is to merge the Wilcox K-omega model, which is good for modeling the near-wall region, and the K-epsilon model, which is good for the free stream in the out part of the boundary layer. And in the SST model, the formulation for the eddy viscosity has been revised. And from the example in research and in industry applications, this SST model is one of the most popular models. Soon after the various turbulence models, the research activities in this field has realized the limits of the turbulence models. Hence, a lot of research had been shifted to large eddy simulation (LES) in earlier 1990s, and later to the hybrid lens LES modeling, according to the reference 1. It is well known in LES, large energy carrying eddies would be resolved numerically, and only the small eddies are needed to be modeled. Generally speaking, these small eddies would be more isotropic, thus it would be easier to be modeled, at least in principle. The LES model was first proposed by Smoklinski for atmospheric research in 1963 and its first engineering application in 1970s. At the late 1970s, a research group at Stanford University took the lead in the development and application of LES. However, LES applies a severe demand on computations, in many cases well beyond the general practical applications. For instance, the computation of LES would be proportional to the Reynolds number per 1.8 to 2 point. So, for the practical application in high Reynolds number, for instance, for a car or an airplane, the LES mesh would be 10 power of 11.5 and the time steps would be 10 power of 6.7. Currently, the large computation of CFD would be roughly 10 power of 9. Thus, the pure LES modeling are still very limited to the simple flows at low Reynolds number, and primarily used as the research tool for studying the details of the turbulent flow. To ease the great demand in LES, Spara proposed a hybrid lens LES model. He named the hybrid model as detached Eddy simulation model, DES model. And this hybrid method becomes a very popular approach, especially in the research community. The hybrid lens and the LES model. So the original DES was proposed for the boundary layer would be treated by lens, and the region of the massive separation are treated with LES. Therefore, the reduced computation can be significant. The mesh now is 10 power of 8 compared to the requirement in LES 10 power of 11.5. The time steps is 10 power of 4 compared to 10 power of 6.7. And now many different hybrid lens LES model has been proposed and being tested. One important issue is on how we can better implement the hybrid lens LES model and solve some challenging issue in the hybrid lens LES model. Using hybrid lens LES model sometimes can be very tricky. Generally, LES could have some very similar mathematical equations as those in lens. Thus, the numeric implementation would be same as lens model according reference 3, and even easier according to reference 4. In some cases, people would like to perform a conventional LES on a coarse grid for the wall-bounded flows, especially in the attached flow region. This approach would be very erroneous, since this type of the LES would be inferior to even simple conventional lens modeling. So when we use LES, we need to pay a lot of attention on the grid.